Alright, we're back for part 2 of these videos on the 24 and 36 volt motor controller. If you saw the previous video, you'll remember that I mentioned that I designed it based off of a cheap scooter motor controller. And the one that I used as a reference was this one right here, and as you can see it's already missing parts because I gutted it. These three, this one, and this one, all operate in pretty much the same manner. They use an LM339 quad comparator. And basically all they do is they take a triangle wave and compare it up against a varying voltage which would come from the pod or the hall sensor, and they turn that into a pulse width modulated signal that feeds the MOSFETs and controls your motor. These are two of the ones that I've gotten from a couple of those cheap scooters, and these are pretty much identical with like a few minor differences. As you can see, there's the LM339. What they do is they take the 24 volts from the battery and they step it down to 5 volts using just a little Zener diode, which this one has right there, across a 2-watt resistor. And that drives all the electronics, and the 24 volts goes, the positive goes directly to the motor, but the negative is switched through a MOSFET. And as you can see on the bottom of this, it's got one MOSFET and one diode, a dual diode. So all I basically did was take one of these designs, and this is pretty much the exact design as these right here, except that it's a single-sided board, and it had a few slight differences, but the working principles are pretty much the same. I reverse engineered it. I made a schematic with it that I'll actually link down below, and I'm going to show you guys here in a bit. And just beefed up the outputs and beefed up the transistors that drive the MOSFETs. On this one here, these three devices down here labeled V1 through V3 were actually two MOSFETs and a dual diode right here. These two big jumper looking things right there are actually just shunt resistors, and it measures the current from there across the motor to either allow it to function or to limit the current. So that's these. These are pretty common apparently. And there's this other one that I've come across too. This one's also from it's another small scooter. These were like a Sunel brand scooters. They use these little tiny controllers. This one was from a Razor brand scooter, so I thought this one was like some really fancy design because it was so small. I mean, the box itself is like pretty tiny compared to the other ones. But to my surprise, when I opened it up, it's just a relay. I mean, it's got some transistors and stuff, but that's just to drive the relay. And I think maybe there's something in here to, you know, kind of like limit current to the battery or something. But that's all it is. So this one's like apparently just either on or off. So kind of a bummer there. And then there's also this one that I got from a small electric bike. This one's actually a little bit more fancy. And if I could open it up, you can see it. It's a little rusty because it actually sat in some water for a while, and it had rain outside, I didn't know, and water got kind of logged in there, so that's why it's a little rusty. I tried to clean it as best as I could. There was a pot right here that got damaged, so I have to replace that, but I'm pretty sure it still works. This one only uses a single MOSFET here, and then it's got the other dual diode right there. This one's using a PIC microcontroller. It's a 16C712. So this one's got a little bit more smarts to it, I guess you could say, than the other ones do. And it also, this one's got like a soft power. The other ones had, you know, like a little physical switch that you had to turn on and off. This one actually has a little push button that you would use to turn it on and off. And then it's got this relay here that cuts power to the motor, but it doesn't actually, it's not the one that, you know, controls the motor speed. That's actually done with the MOSFET. So yeah, this one a lot fancier than the other ones, and I'm sure it's got, you know, better current control or current limiting and all that stuff, so not bad. Okay, so how my motor controller actually works. As I said, I reversed engineered this one and I came up with the schematic for it, which is this. I've only left out the numbers from these the two MOSFETs right here and the transistors because those were the ones that I was going to be, you know, changing, so I didn't write those out, and I don't remember exactly what the originals were. And then these two right here would have been those shunts, which also, you know, if I'm going to be using current limiting, I would have to figure them out, calculate some sort of resistance that, or resistor that, you know, would work for what I'm doing. But all it does is we've got the batteries over on this side, 24 volts. It goes to a cap. Here's a motor. The negative of the motor goes directly to the MOSFETs. All the MOSFETs doing is switching the negative lead from the batteries to the motor. So that's the whole output stage right there. That's really simple. And here's the dual diode. I did write this one down from the original. It was an MBR 2100. So we got 24 volts here. Here's the power switch. That doesn't do anything with cutting power to the motor. The motor's always connected to the battery. The only thing that controls it being turned off is the MOSFETs. So we turn the power switch on. We get power flowing through this little resistor divider right here, which feeds the two drive transistors. The whole purpose of this, and since we're doing 10K and 10K here, then we get in half the voltage. So this one right here would be about 12 volts. The comparators inside the LM339 can only sync current. So we need something to raise the voltage up to allow the NPN transistor right here to start conducting to turn on these MOSFETs. And when this switch is turned off, then we've got the other resistor down here that basically pulls this all to ground. It should be basically activating this PNP right here, and it's just grounding out the MOSFET, so nothing's getting driven. You can't do anything when the switch is off. We've got the 24 volts going through a 50 ohm half watt resistor here, and that feeds, that's this Zener right here is connected in parallel. I accidentally used the symbol for a Schottky. I didn't realize it until afterwards, but yeah, that's supposed to be a Zener diode. So that holds this whole section up here to 5.2 volts. In my design, I'm not using the Zener because I'm using the switching regulator, because I plan to use it for more than just powering the electronics. We've got 4 different sections here. We're using each one of the 4 comparators inside the chip. The first one right here is actually a triangle wave generator, and we'll see that once I start probing the board. All this does is it generates like a triangle wave to compare to a voltage that's coming from the Hall sensor, and that's what we got here. This comparator right here is the one that takes care of doing the pulse width modulation. So we'll see this a little bit more clear later on, but basically what it's doing, it's comparing the voltage on the triangle wave to the voltage on the throttle. When the voltage on the throttle exceeds the voltage on the triangle wave, then it turns this output, or it allows this output to float, which gets pulled high by this resistor right here. So that sends a pulse to, or it sends a positive voltage to the NPN diode right here. It turns the MOSFETs on. When the voltage on the throttle is below the voltage of the triangle wave, then this output gets synced, and it's basically this whole section is turned off. So depending on how much the voltage coming from the throttle is compared to the voltage there, then either the pulse gets wider or smaller, to be turned off. This brake switch right here, which is the one I was talking about in the previous video, basically what it does is it pulls this line to ground. So no matter where the throttle is, it will not, the voltage on this line here will not increase, at all. So it basically keeps it grounded, can't switch these transistors, can't do anything. And then we've got 2 more sections here. This one is the current sense section. So we've got this lead coming off of here from the current shunt resistors. If the motor here is stalled, it's heavy load, whatever, it's taking a lot of current, then more voltage is going to be generated here at these shunt resistors, and that's going to come all the way over here, goes through a little resistor. It's got a little cap right here for smoothing, and that's right here on it goes to the negative input. So there's another current divide, or another voltage divider right here formed by these 3 resistors. I don't know what the specific voltage is right here, but it's really tiny. It's something really tiny. It's just once the voltage from here exceeds the voltage in here, then this gets pulled low, and once again it inhibits the number 2 comparator right here from operating, so it can't do any switching. So that's how the current limiting works in this particular circuit. And the last one right here, number 4, is just a it senses the voltage from the batteries, so that if it drops below a certain voltage, which is set by these 2 resistors right here, then it shuts this off again. So basically the way to stop this is to just make sure that the input right here on the number 2 comparator doesn't exceed the voltage from the triangle generator here. This one's always oscillating. As long as this is turned on, this one's always oscillating, generating a triangle wave, and this one here is comparing it against the voltage from the throttle. And as long as, you know, none of these, this one, or the button here, well, switch, aren't grounding out the positive input here, then this one's allowed to operate and compare the voltage from the throttle against the voltage from the triangle wave generator. Okay, on the board here, I've got 3 little points labeled with these little dots here. We got the blue one here. This one is the output from the pulse width modulating comparator. We got the green one here, which is the input from the triangle wave. And then we've got this red one here, which is the input from the throttle. And it's also the one that takes the inputs from the current sense comparator, and also from the voltage one. These 2, as I said, are not really doing much at the moment. I mean, the battery one is, but not the current one. You can see that there's a little pad that I've left open right there. That was so I could have a, you know, like other ways to shut this circuit down in case, you know, certain values were exceeded or whatever, but it was never put to use. As I mentioned, I'd never quite got around to finishing up everything how I wanted to. So let's take a look at the setup here. I've got all the power connected to the motor controller. I've got positive coming in through this 10 gauge lead here, and then I've got ground through this piece of 8 gauge. I don't have any motor connected to it right now. We're just going to use this resistor right here as a kind of a load, just to do some waveform testing. I've got the starter motor back here that's ready to go. As I said, we're going to be testing this for the first time. Except, only problem is, the only power supply that I've got right now that I can use for this is this Pulse SL20. It puts out 24 volts at 20 amps, and that's basically only going to give us about 480 watts. Although, on the side here, this power supply says it's capable of a peak power of 600 watts. So, I don't know. This, not quite exactly what I would have wanted. But the only other option I have is some car batteries, and I guess I kind of have those on standby in case we can't really go anywhere with this. If it overloads this power supply too much, then this motor's probably not gonna spin, and I'm kind of thinking that that's what might happen, so I may have to resort to using the batteries. I don't know yet, but we'll give it a shot anyways with this first. If that doesn't work, I'll bust out the batteries, I'll hook everything up, and we'll, you know, try it that way. Another thing that kind of sucks is that I'm kind of using inadequate wiring here. I mean, I only got this, what is this, like, probably like 10 gauge, even though the jacket itself is fat, the wire is only about like 10 gauge. Whoops, I just shorted something out, but nothing happened, so it's okay. So then I've got that hooked up to one of the nuts back here through one of these ring terminals. And then I've got these other 10 gauge pieces here. These are connected together right here because this blue one and the yellow one are for the field coil on the just knocking stuff all over the place here, making a mess. Those are connected to the field coil in the starter motor. And then I've got the yellow lead here. That's the one that's going to connect to negative once we get around to it. Alright, so enough chit chat. Let's go ahead and take a look at some waves here. Alright, so the first waveform we're going to take a look at is the output to the motor. What I've got here, as I mentioned, is this resistor, which is acting as a pull-up for the output, because the only thing we can do to control the motor is to pull it down to ground, or negative, as it's here. So I've got my lead connected to directly to the output, which is that side of the resistor right there. This resistor is only a 68 ohm, which, I mean, doesn't really need anything critical to do this test. It's just a really simple test. Alright, so on the scope here, I've got the ground set to this line down here on the bottom. So when I turn it on, it should jump up to about right there, because it should be getting right about 24 volts. So I'm going to plug the power supply in, And since that lead on, or since the probe is connected to the resistor there and it's getting pulled up, it should jump up to about 24 volts. So power supply on, and there it is. It's measuring about 23.5, so I mean it's close enough. So let's go ahead and increase the throttle here, and we'll see what we get on the scope here. So as I said, it pulls down to ground, so we're gonna see there it goes. As you see, it's when I have the throttle just barely pulled, it's only pulling down like a little bit, or like a fraction of a wave there to ground. And then as I increase it, it starts getting wider and wider down at the bottom. So it's increasing the duty cycle on the motor, and it's operating a higher percentage of the time. So, and then if I release it, it starts shrinking again until it stops getting switched. It stops getting completely switched. So if I go all the way up, eventually it's all the way on. So now the motor's receiving the full negative from the input. And again, release it, it goes back down. So off, no more switching at the output. So now we'll take a look at those 3 points on the board there. Let's start off with the green one. We'll show the green one first because that's the triangle oscillator. Okay, I've lowered the voltage to only 1 volt per division because the voltage the voltage on that triangle wave is not very high, so 1 volt per division should be more than enough. So here I go. I'm going to touch the lead, or the probe, to that trace, and there you go. You can see that triangle wave right there. I don't know why it's flickering so much. Let's turn it up a bit. Let's increase the time base here to 20 microseconds, and there it is. So as you can see, the wave, the bottom of it doesn't exactly hit ground. It's resting slightly above. Let's see what voltage that is. So it's at about 1.22 volts there, and it goes all the way up to 3.76. So we'll leave this here, and I'm going to move the probe over to the input from the Hall sensor. As we can see, it's slightly above ground as well, but it's not quite to where the bottom of that triangle wave is. So when we start increasing the throttle, it has to get to about that point before it actually starts pulse width modulating. And then once we exceed the top of that triangle wave, which would be, let's see, let's mark it here, should be about there. Once it exceeds the triangle wave completely, then that means it turns the output all the way on, as you can see right there, and then the MOSFETs are just continuously switched on, and the motor's receiving the full voltage from the batteries. I mean, actually the motor receiving the full voltage from the battery anytime it's switching, but because it's pulse width modulated, then it's only receiving it at like a fraction of each cycle. So I wish I could have 2 probes on here right now. Let's take a look at the output. I'm going to hook up the probe to the output right now. So I've got the throttle all the way down. Probe is connected to the output of that comparator, and as you can see, once we start increasing it, it starts generating an output, or it starts allowing that output to go high, but the voltage on there is a little bit higher, so let me lower this a bit down to 2 volts per division. So there it is. It's not exactly square, and I think that might be due to because of some of the resistors values used here, but it's enough to allow it to work how it's pretty much supposed to. So right there, it's got a tiny bit of throttle. You can see that the on time is very tiny. As I start increasing it, the on time becomes even longer and longer till eventually it's fully on. So that's the output from the comparator going to the transistors. From the output from the transistors driving the MOSFETs, I've got it hooked up there right now. As I start increasing it, you can see that that kind of follows. So this is the one that's switching the MOSFETs on and off. So that's all it is. I mean, it's very basic in operation. All it does is it just compares that triangle input to the input from the throttle. So let's I guess let's go ahead and connect that starter motor now, and we'll see what happens here. See if things go up in smoke or if we just get nothing at all. I'm not sure what's going to happen, but let's give it a shot. Okay, here we go. I've got the motor all connected. I just took the wire and just kind of looped it in there so that I could clamp it in with that nut. So here we go. Let's start increasing the throttle and see what happens to the starter. There it goes. It's working, but I think I might be hitting some of the limits of the power supply there. Let's run it for a bit at maybe about half throttle and see if anything warms up here. Wow, that's actually working pretty well. That's throttle all the way up right there, and it's holding, but the overload light on the power supply is on. But wow, that actually did a lot better than I was expecting. These plates are probably, or these bars, aluminum bars, are probably going to take a bit to warm up. But the wires aren't really getting hot. But then again, I mean, like I said, we're kind of limited by the power supply. If I had some batteries, we could probably do a little better. But yeah, I mean, it held up. Let's go open throttle from close and see what that does. Okay, yeah, the power supply can't handle that. But I mean, it's handling it. So you know what? Let's hook up some batteries. We'll do the batteries. Okay, here we go. We're playing with power now. I've got these two batteries. They're not in the best condition, but they still hold a charge. And we've got a total of 24.86 volts out of them. I've had to resort to using hose clamps to hold the wires on because I don't have any battery terminals that I could use there. In the back, I've got four big chunks of wire there, like clamps, so you know, just to make sure that I can handle the current. And this all stayed the same. Here we go. Got power, got our motor. We should probably put the camera on the tripod because I'm going to need to probably keep a handle on that motor so it doesn't go crazy, just in case. Alright, here we go. Yep. Okay. Yeah, it definitely responds a lot quicker with batteries. I think the only limitation we probably have now is the fact that these wires are, you know, like way smaller gauge than what starters usually use. Like, you'll have a really thick cable going to your starter, and then the casing, you know, is grounded to the engine. So I think that's where we're hitting some limits right now, and maybe also these MOSFETs, I'm not sure. But I mean, it's holding up. And you can actually start to feel these warming up now. I mean, they're not that hot right now, but yeah, they're definitely starting to warm up. But well, I guess overall I'm kind of happy. It's working as intended. It's holding up. It's not frying as soon as you hit the throttle. So, well, you know, this could have been done a lot easier, especially nowadays with like Arduinos and stuff. You just program it so that it's got the PWM output going to, you know, like a MOSFET driver or something, and then driving your MOSFETs. But I built this with just the parts that I had like readily available. I had a bunch of these MOSFETs around from some old UPSs. These are IRF, I think they're IRF 46 MOSFETs. So I had a bunch of those. Like I said, I used 16 of those. The only thing I really ordered was the diodes. But I mean, that wasn't super expensive. And then everything else I just kind of repurposed from the other motor controller like I showed, and then I just, you know, built the rest of this. So this was actually done on the pretty cheap. So anyways, hope you guys enjoyed this. If you like it, make sure to thumbs up, subscribe, and all that yada yada yada. And thanks for watching again, and I'll see you guys next time.